tengan miedo de preguntar, esta es su oportunidad, ya se les van los speakers, ¿eh? No hay preguntas malas, y hagan todas las que quieran y puedan y se les ocurran, no importa. Déjenme ver si ya está listo. Okay, now we have the last lecture of this workshop and of Priscilla, and she's going to finish with the challenges in direct dark matter detection backgrounds.
Okay. So you can basically divide the backgrounds. Obviously, for direct detection of dark matter, the whole story is reducing backgrounds so that your sensitivities can be better. And you can divide those into two types, cosmogenic and radiogenic. So under cosmogenic, we have cosmic rays and any secondary reactions caused by those cosmic rays, and activation products in the shield and the detectors, by which I mean often people use for the second one, they call it cosmogenics, meaning you get these lines in germanium that are caused by them being above the surface, for example. Radiogenic, by that I mean external natural radioactivity in the walls and structures of the site, radon that you have in any underground site, and then internal radioactivity, which I mean what's inside of the shield and construction materials. This is something that all of these experiments have in common as one of the things they have to work very hard at, which is why I'm spending a little time talking about the devices that these detectors need to use to screen and assay their materials to make sure that they can be used in the experiment. Specific to each detector technology, of course, are specifics that have to do with their particular materials that they're using, and any naturally occurring radioisotopes that come with their target material that another detector doesn't have. And I just thought I'd start by setting the stage, and I don't know if this is a class, maybe some of you can answer these questions. Do you happen to know, for example, how much radioactivity in becquerels is in your body? Anybody have a guess? What do you think? 1? 10,000? So, somebody say something. What do you guess? 7.1? 7.1? You're off. About 4,000 becquerels from carbon-14 beta decay and another 4,000 from potassium-40. And that means that you are right now bathing this room, each of you, about 8,000 neutrinos and 8,000 electrons and some gamma rays every second. How many radon atoms escape from the ground per square meter per second? So as you see, I'm not going to go on until somebody says something. What? All right. So 7,000 of them per square meter per second. This one you probably do know. Somebody know what these are? The natural fraction of radioactive potassium, carbon. I just go on, that's kind of boring. Anyway, here it's about 0.012% of potassium is a radioactive component. And that's, of course, why when you have bananas for breakfast, you're a little more radioactive than normal. And carbon-14 is in the PPT section. And every time you take up some soil, of course, there's some places where there's more than others, but on average, if you take a kilogram of soil and you look in it, how many plutonium atoms? Don't say 1. All right. 10 millions. It's the transmutation of U-238 by fast cosmic ray neutrons. Okay, it's just happening all the time. Plus, soil itself has, and because of that, I mean, the reason that that happens is that you have already 1 to 3 milligrams every kilogram. You have uranium in the soil. So that makes life hard if you don't want any of that in your detector. So we have several lines of defense. I'm going to start with the cosmogenic backgrounds. Okay, so these are basically, let's start with cosmic rays. And so you can see the muons. If you go, you don't have to go actually very far to bring it down several orders of magnitude. And in the end, though, of course, you reach at some point a place where you are now approximately even to the number of neutrons produced by the fission and alpha N interactions around you. Neutrons are actually produced by those muons as well, and you'll note that as you go deeper, you don't get rid of the neutrons as fast as you get rid of the muons, which may be a little important later. Anyway, you go deep underground. That's why we have underground sites. That we also include passive shielding and active shielding. The passive shielding is good to get rid of the radiogenic material that's coming from the walls, because the neutrons from those are fairly low energy. But the cosmogenic neutrons, in other words, the cosmic rays that are making the neutrons, those neutrons are high energy. And so you need to work a bit harder with your shielding. And in fact, it may not be good enough, because the moment that you put any shielding on, of course, you have some of the radiogenics. So if it's not good enough, you also use active shielding. If you're not deep enough, you might put a muon veto around your detector so that you can tag those muons that are making the dangerous neutrons. And they're dangerous. Neutrons are dangerous for most dark matter experiments because they look like nuclear recoils. So they're our main. We can often figure out a way around understanding the difference between what an electron recoil and a nuclear recoil looks like, but it's very hard to tell the difference between a neutron and a WIMP interaction on an event-by-event basis. And finally, this is very important. Oh, I'll talk about this later. This is very important too, which is that we get down to a point where we're talking about one event per year. So simulation to understand actually what we believe our background is extremely important. These are just some of the underground labs. And you can see how the muon intensity goes down by order of magnitude until you get to the deepest one, which is the one in China. Sudbury is quite deep as well. Note, though, that as you go deeper, your spectrum of muons gets harder. So the average is around 200 JeV, and it's down at 350 JeV at Sudbury. So it's not just enough to talk about getting the muon intensity down. So here's a cartoon, and let's look at all the different ways that the muons are bad for induced backgrounds. So you can have a muon that gets through, and actually, so this is your detector, this is your shield, this is the cavern. So a muon can interact with your shielding and produce a neutron. It can interact all the way down through the rock, and eventually near about, I'd say, a meter or two. We've done simulations, and we know that the showers that get through the rock start somewhere between 1 and 6 meters in. So you don't have to actually use a simulation to work on the showers that are 10 meters in, because by the time the 10 meters are over, nothing gets in. So you'll need to do some work here in the simulation for about at least put in 5 meters of rock there and see what secondaries you get. A muon can go directly through your detector itself. So if you put a muon veto around the detector, of course, what you can do are tag these 3 types of events. And so even though you have all the shower particles, you've already said, I don't pay attention to that event. However, you do have these other muons that come down and produce a neutron, and the neutron sneaks in, and if this is your regular muon veto, usually you're not sensitive to neutrons. So this is the main background that people have to simulate, because it doesn't happen very often, but it's the one that does get through. Another strategy is to do something called an umbrella muon veto. So instead of just putting something close around your detector, put something as large as you can, because that will take care of some fraction of these as well. And finally, you can make an active detector. So this would be like a neutron veto, maybe. The advantage is, of course, this is sensitive now itself to the neutrons that come in. A disadvantage is it's not so easy to make one of those. You can make a Cherenkov device. Liquid scintillator is popular, or some neutron capture material like gadolinium-loaded material like liquid scintillator, or helium. So here's some shielding examples. This one is from CDMS. This one is from Lux. They're very similar. You start out with some sort of, well, for Sudan, we had our muon veto right here. So it's not a neutron veto. It just tells us, just tagging the muons. And in fact, our shielding for SNOLAB does not have a muon veto because it's deep enough, we don't use it. The next thing that happens for both of these cases is a large quantity of hydrogenous material, which is basically either poly or a water tank in lux. And this gets rid of these low energy neutrons that are coming in from the cavern walls. Next comes lead, and I guess they just have such a whopping big water tank that they can also get rid of some of the gammas through the water. If you want a more compact shield, you'll use lead to get rid of the gammas, and then more poly or more hydrogenous material to get rid of anything you produced in the lead on its way in. And hopefully by this time, those high energy neutrons have been moderated in the first layer of poly and then gotten rid of in the second layer. And anything that comes close to your detector itself is made of something that's high purity, either titanium or copper. The dark side strategy, this is a picture from dark side, this is their active veto, and it consists of a 30-ton boron-loaded liquid scintillator, spherical veto, that's here, instrumented, you see with all the PMTs, and then outside of that, so imagine this is that thing, outside of that is a water Cherenkov detector. They are planning for a multi-ton scale liquid argon experiment, and they're at moderate depth in Gran Sasso. So they sort of have to do that. It also not only works on the radiogenics, but it also reduces any risk due to any contaminants they might have in here that they thought they got rid of by screening but didn't. Trouble is, of course, it does cost money, and it's huge. And if you have an underground site that's rather small, you might not have that luxury, and you might not need it. So Panda X, for example, has a very compact shield, and they don't go for all of this active V because they're very, very deep. In the end, though, those neutrons that still sneak through, you need to have a reliable cosmogenic simulation, which is usually done in GEONT 4. Now, early on, there was a very nice paper by May and Heim where basically they looked at lots of different underground sites and depths and parameterized the spectrum. So you kind of see the red here, bends over sooner, comes down here. WIP is a very shallow site. As you move deeper, the spectrum moves out and becomes harder. And then from that, they gave a set of curves. And many people use these curves to determine what their backgrounds are, and they didn't do a good job with it. Several reasons. One is, for example, this assumed a flat overburden, which is clearly not true. Here's just a picture of the geology of Gran Sasso. But also, you have to track every secondary particle in the shower. You cannot simply do some sort of grabbing individual particles from some parameterization because you don't get the correlations between the particles in the shower, and you don't get the as many as you need, and you actually make grave errors. It's correlated with energy and process. Oh, and then if you grab your neutrons from this and you don't continue with your muons, you miss the fact that some of those muons hit the floor of your cavern and produce neutrons going up and other things. So.
And also in that one also depends on the type of rock, right?
Yes. Then there's
the overview.
Absolutely right. So, for example, Sudan has iron deposits. So for Sudan, that's the interesting point, is that for CDMS, not only did we do GEONT, but we didn't even use a parameterization for the muons that started at the surface. What we did was we took data from the old Sudan proton decay experiment and from Minos that were running there, and they had azimuthal and polar angle information on the flux of the muons. And so those we converted into path lengths through, or sort of for each direction we had a slant path and the amount that we reduced it. So we actually built a model that was in azimuth and polar angle what we actually get at Sudan, which we do not have to do at SNOLAB because SNOLAB actually is A, very deep, and B, does have a flat overburden, basically. Sudan didn't. It was on a ridge. And then there were the iron deposits as well. It's actually a big success story because about a decade or maybe more, the neutron fluxes from the two programs that were in use, FLUCA and Géant-4. It's good there were two in use because they actually disagreed with each other, which made people understand that there were some real issues in the physics of producing these neutrons from the muons. So the muon nuclear model itself and cross-sections were just not updated, and there were a number of things. And now uncertainties are reduced to 5%. This has been an effort over many years and has included people from FLUCA and people from Géant and people from various experiments. But to get any better, you actually need data, and it's very hard because you're talking about what is actually happening underground with the neutron flux, which is very, very low. And so any experiment takes many years to actually get enough data to benchmark your Monte Carlo, because that's what you really want. You want some data to compare to your Monte Carlo that isn't the data in the experiment itself. So there are two experiments that do have data that has been used. One of them is LVD at Gran Sasso, which is this enormous structure, which is basically stainless steel and liquid scintillator modules. And they made measurements of neutron yield in liquid scintillator and in stainless steel. So another thing you need for the various materials, you need that. And some of this can be done by in an accelerator, and people do have muon beams and that kind of thing, but typically only for a certain energy and not for all of the materials you want. And their comparisons with Géant went from basically 30% for version 9.3 to 9.5 being much better. Another one is at Sudan, and this is, these are proportional tubes that you see. The whole, it's like being inside of a huge muon tracker. All the walls are covered with these proportional tubes, which used to be the veto for the proton decay experiment that was there, which was removed, but the walls were left and refurbished, and a modern data acquisition system was put in. And then this device was put in the middle of it, which is a gadolinium-loaded scintillator, actually water with some wavelength shifting material and gadolinium. And so what happens is that the muon comes down and well, actually, the muon makes the neutrons. So what you're trying to do is you're measuring neutrons that are coming in. So you'll see a muon, and you track the muon coming through these walls. There's a neutron accompanying it. The neutron makes it into the neutron multiplicity meter. What it really does is it goes all the way down here, makes secondary neutrons. Those secondary neutrons are slow enough that they get captured in the gadolinium-loaded scintillator, and the high-energy gammas that are released by that capture get seen by these phototubes. And it turns out that the number of secondary neutrons liberated per primary neutron is correlated with the energy of that primary neutron. So you actually get a bit of a spectrum. It's very crude, but you get some. And so again, these are the only two experiments right now that have data that inform us of that. Then we have something called activation products, and these are very difficult to calculate from first principles as well, because we're talking about some material that's on the surface of the Earth for a certain amount of time. The cosmic ray spectrum varies with latitude. The isotope cross-sections in the process of this spallation or whatever particular process that's going on at the time, often neutron capture, are just not well known. So what can you do? You can avoid it. And to do that, you want to put all of your materials underground that have cosmogenic channels. Not everything does. So for example, if you use material, well, I said silicon here, but now we know that there is a cosmogenic product, but it doesn't have to do with leaving the silicon out in the open. It has to do with the silicon-32, which I mentioned earlier as being one of the major backgrounds in very sensitive silicon detectors, is actually produced in the atmosphere, and it gets brought down with rainwater, and then it seeps into the ground, and then the silicas that you're going to eventually turn into the sand, basically, that's going to be your detector, gets impregnated with this water, and over time it gets the silicon-32 in it. So it's basically argon in the upper atmosphere. And neutron capture. Okay, and then of course transport, Majorana has done a lot with understanding how they're going to transport their germanium double beta decay detectors from PNNL where they're made up across the surface and then down into surf. And so actually found out that iron is the best protector of those, and you still have to count how long it's been in that above surface. And of course you can try to subtract background too. That's what this picture is. I showed it to you before. Again, it shows you all of these activation peaks that are in the germanium of cogent. The better your energy resolution, the better able you are to distinguish what those are and no longer think of them so much as a problem as even a calibration source. And one way to think of it. Okay, I don't know that we need to go in great detail through it, but you can see what gets produced in germanium. So you do have tritium getting produced in the germanium, for example, and after 30 days of surface exposure, and then you take it underground for 1 year, and it slowly, depending on the lifetime of each of the isotopes you've created, they slowly can decay away. And some of them, of course, are not such a problem. Just bring it underground, leave it for a while. Others are more of a problem. And it's not just your detector. Copper is great, except if you leave your copper above ground, you begin to have all of these isotopes made inside, which then produce gammas that get into your detector if you try to surround it with copper. Radiogenic backgrounds, there's the external ones. So that's, basically not just the cavern rock, but then you go and you spray shotcrete all over, say, the rock at, which is Ely Greenstone is the rock that happens to be at Sudan. And the first thing people did when they made a big cavern there was to spray shotcrete. You know what that is? That's that concrete stuff that basically keeps the rock from flaking off on you, and it makes a nice surface, right? And it was worse than the rock. Much worse. It has a lot of, shotcrete, it's concrete, it's got a potassium in it like crazy, and so nowadays I think SnowLab has a kind of vinyl surface. Do you know what it's called?
The shotcrete? Oh.
No, what you use at SnowLab.
It's shotcrete.
They call it shotcrete too, but it's obviously a better quality of shotcrete, right?
Well, okay.
But then they paint it?
Yes, that's why.
And that helps a lot, and that's a radon impermeable?
No, actually,
okay.
Only there's no cavity, but it's no lab. It's interesting because the old areas of the lab, the shotcrete is low radioactive, has a low amount, but the new areas
has worse.
You could see because we measured the gamma flux, and it is higher. It's like 50% higher, and it is the shotcrete that
yeah. So it's not enough. For example, to have to say the word shotcrete, it's going to depend on the vendor, it's going to depend on composition. Everything needs to go through some sort of assay. So you can see all of the kinds of cautions that we have to take for that. I don't think there's that. Well, radon, prompt radon daughter means so having radon, which just gives you gamma rays, and it's not a problem usually because you can put some sort of radon barrier around your device and purge it with nitrogen and keep the radon out. I'll mention later something called radon plate out, which is a far worse problem. Yeah, and this is just, I don't think there's much more to say here. Oh, right, this is what I look like. This is great because we shielded it. But shields always introduce some sort of internal background as well. So, there's the usual uranium-thorium chain, but you also have, and salts like potassium, but you have things called anthropomorphics. So, antimony and cesium from the 1950s, bomb test residue is in water that you use to clean your devices. and some places are worse than others. And it's, any pollution, often depending on where that pollution comes from, can be bringing in particulates that themselves are loaded with a beta emitter. And then, of course, your specialized target material itself might have a naturally occurring isotope, which is what happens with argon and xenon. So argon will have argon-39 as the thing they need to get rid of, and xenon has krypton-85 as the thing they've got to get rid of. That's inside of their target material right from the start. Lines of defense, of course, are to screen everything. Also to purify materials, and just to make sure that you did this right, to detect all your backgrounds in situ. So here's the thorium chain. I'm going to look at thorium, then uranium. So here you have one of the radon gases, 220. It doesn't last very long, so it doesn't get very far. Basically, it's produced, but it's usually not so much of an issue. It is, however, responsible for a sort of non-equilibrium between in the chain between gammas that you get from actinium and from the bottom of the chain. So sometimes when you have a material and it's got some trace thorium in it and it's been going through this chain, if you just trust the gammas from one of these elements, you might get it wrong. You need to look at the whole picture, which is usually done with a high purity germanium detector, and see the whole chain and try to understand the non-equilibrium situations you might have. The uranium chain also has radon, but this radon lasts for about 4 days. So it moves around and it gets other places, and then it settles on them, often along with it might get onto a piece of dust, and the dust falls down on your material. And then it becomes lead-210, which sticks around for about 22 years. So 22 years ago, when somebody was creating a piece of material you plan to use for your detector, it could easily have been coated with this 210. And the cleaning is not necessarily sufficient. And the reason that cleaning it isn't sufficient is because that 210 lead can then have an alpha decay, and the energy of that alpha decay can push that nucleus into your material deep enough. It's that just a simple surface cleaning with alcohol or anything else is not enough to get it out. And now you've got a device that's basically radioactive. And this can also happen here. That's called radon plate out, by the way, if you hear that word. All right, so for example, this was an example of these lead recoils in CREST. I think I mentioned this last time. So here is a yield plot for CREST where you have the electron recoil background up here and your two nuclear recoil bands, oxygen and tungsten, and alphas show up here. These events here are known to be they're very low yield, and they're actually not the tungsten, they're lead recoils that I've got a better picture here from contamination in the clamps. So here's a better picture if you want a kind of cartoon of what's going on, either in the crystal itself, the lead, in this case it's 206, gets pushed in, or you get an alpha decay in the clamp material and that lead 206 nucleus travels across to the target crystal. And then you're not looking at alphas anymore. I mean, the alphas were easy to tell, but now you've got this really well quenched nuclear recoil that, if you're not careful, can be a problem. We also have lead recoils in super CDMS, and we actually use them to do one of our calibrations. So here is a picture of the field shaping we do to get rid of surface materials. So this is a bulk interaction where you have the electron and hole pair to opposite sides of the crystal. Here's a surface event where it only goes to one side. Let me look at the picture first. So if you put a source on one side and then you plot side 2 versus side 1, all the bulk events are there in the middle, and you can make cuts here to get rid of anything that's on the surface. They'll only show up here. But we actually made little wafers that were implanted with lead-210, and the way we did that was just stick those wafers in a box with radon. And we let it plate out, and then we had sources, and these sources were used to give ourselves a lot of surface background. Usually we don't have that much surface background. We put enough surface background on there, we can actually decide how well we reject surface backgrounds. So that was the whole point of this exercise. This is a picture now of a yield diagram for the super CDMS detectors. What you see are the electron recoils here. What you see here are the surface events, but that are produced now by a source. And way down here you see the lead recoils also. And this is the band where we're expecting to see our neutrons or our WIMPs. We don't have neutrons in this particular picture. Here we do. Here's a neutron source. And now this is our asymmetry cut, side 1 minus side 2, pulls all of that stuff to the side, and we can easily not only identify where the neutrons are, but because we have so many of these, we actually is how we found out that our rejection of surface events was at the level of 10 to the 5. 1 in 10 to the 5. Here's our uranium chain again. Just a spontaneous fission is another source of neutrons. So any materials you have will have some spontaneous fission, which produces neutrons. And alpha N interactions will do that as well. So you have an alpha. You say, I don't care about alpha decays because I can recognize an alpha in my detector, but sometimes the alpha just interacts with your shielding material and produces the neutron that you can't see. And for this, it's very important to use programs like Sources and Talus in order to provide the neutron yield and spectra. And so you typically do screening of your materials so you know how much uranium, thorium you have, and you input that, and you look at the alpha decays and use sources, these programs to understand how many neutrons are produced from those alpha decays in your shield. I don't know why I said that. Okay. That's true. Doesn't seem to be very important right now. But in any case, screening materials is the next thing I wanted to talk about. There are a number of ways that you do this. The workhorse, these high purity germanium detectors, these are all counting techniques. You put a device inside of a machine and you wait for the decays to happen and you count how many decays you have in a certain amount of time. You can imagine that takes a long time if you're looking at very low activity materials. Neutron activation is actually a counting technique, but it is typically a material that you've activated, and so it doesn't take as long, and so you have a higher rate. Alpha beta counters, radon emanation, and gas proportional counters, and I'll talk about most of those. Non-radiometric techniques are various forms of mass spec, and there's a whole alphabet soup of these I'll mention. Surface analysis, this is something that almost every university has something like this, often used by geologists, or that's, you're going to probe the elemental composition. You can do submicron position and depth profiles. So if you've already identified that there's a problem with your material and that it seems to have an activity you don't want, but you don't know where it is, you can try to find out something about it using all of these techniques. And of course, atom trace analysis, ATTA, you actually trap the atoms, excite them to a metastable state, and then detect their fluorescence. So this is a way to actually count individual atoms, and it's been done, I think, by xenon, but certainly by EXO. And you can measure, this is a way to measure krypton 85 and argon 39 to a few parts in 10 to the minus 14, so it's extremely sensitive. So just a comment now, so let's go through a few of those in detail. High purity germanium detectors really have a range of what they're looking at. They're looking at gamma, so they're only counting gammas. between 10 keV and several MeV. They have excellent energy resolution, and so you can use them to identify your isotope. You can just put your thing in there, and then after it's been in there a month, you look at the spectrum and you say, oh my God, it's got antimony in it. Where did that come from? And then you can go do, you know, your detective work. They're just getting better all the time, and mostly it has to do with improvement of their backgrounds, and it usually takes a long time to do the best sensitive work. The nice thing is that because they do isotope identification and all, you can just take something in that you have no idea what it is, put it into your high purity germanium detector, and in 4 days you say, oh, that thing is much too hot, and you take it out. So sometimes the assay only takes 4 or 5 days. If it's very good, it takes longer because you have to get down to the sensitivity where you actually see something. The commercial, they come in various forms. Commercial ones that you can buy are a few hundred parts per billion of uranium and thorium. What we often use, I call augmented commercial. These are the ones that you might purchase one from Canberra that is already known to be very sensitive, and you make your own shield and you put it underground. Maybe you have an active veto around it, like a sodium iodide Compton veto. And now you're getting down to much better sensitivities, and usually don't do quite as well at actually, well, that's not exactly true. There's a wide range. And then finally, there's this thing called GEMPI, which is basically is just germanium from Planck. The MPI Institute has done a lot of work on making the very best ones, and they're still champs. This is it's an old plot, but it's rather nice because you're looking at the normalized counting rate versus the depth. So you might think that all you have to do is take this germanium detector, put it deeper and deeper and deeper, and you do better. But and if that were the case, you would be following this curve, and in fact you don't. All of these detectors end up sort of maxing out at some sensitivity because it's mostly limited by internal backgrounds in your crystal itself. I don't know how much time is it. Let's say a few things. Let me see these are just the elements of your high purity germanium detector. If you're going to do the very best you can, you will actually, what would be great is to grow the crystals and manufacture them into detectors underground. That is not done anywhere yet. So instead, you make the crystals as quickly as you can with a very good zone refining, fast processing, and you get them underground as quickly as you can and store them there till you're ready to use them. Cryostat system also, they're kept at liquid nitrogen temperatures, and you need the cryostat itself to be made from screened materials, and use a high-grade copper that's been stored underground right after electrolysis if you're using this type of copper. You could also make electroformed copper, which is more expensive but better. So be careful. All of these little details, they all matter. How do you put the thing together? And in the end, you have to do electropolishing of all the metals and acid cleaning, and you have to be in a clean room because you don't want that radon plate out to occur while you're done all this other great stuff to keep it clean. The shield, there usually are two pieces. There's a sample volume, which is made of copper, which is inside, and that's where you're going to put your sample. And then on the outside, you have lead, and as you move outwards, the lead you can have less worry about how good that lead is. But right near the beginning, you often need ancient lead to get rid of the bismuth 210. Right. So you continue to put more layers around, but near the outside, it's not as important. And then you do have to put some sort of box, not necessarily steel, but some box around the whole shield, overpressured with nitrogen gas to prevent the two fears of radon. The prompt radon that just gets in there and just has gammas, and the one that might plate out on your shield just a picture of one of these GEMPI style shields with a sample changer and cryostat over here. A lot of details. There's all sorts of solutions to how you get a sample from a nitrogen-filled sample box through and into your detector without letting any room air in. So usually have a load lock, airlock type of system almost. So we have, sort of state-of-the-art GEMPI detectors in terms of the counts per KeV per kilogram per year. And these are all actually, these are all pretty good. This one is without the shield, just as a way to show what difference that makes.
Oh, and it's already at the level of the height of Moscow,
Yeah.
the background.
Right. Yep. There's actually now a number of these germanium detectors that get down to that level, most of which are at Gran Sasso. So they have a very good counting facility there. And we can talk later about how you want to get a good counting facility underground, maybe in Mexico, maybe in a mine somewhere. And having something that you get to this level with is absolutely doable, and then makes you one of the premier places in the world where such a thing can happen. And right now at Gran Sasso, they have a lot of other customers besides physics. So they do things like, product, what's it called when you label your product with where it comes from? Produit, I don't know, but, so you want to know that the salt that comes in this special thing came from this location just off the coast of France in some place, so that it can be labeled. This is important in France. The other things, and like where your wine comes from.
Or the mezcal, right?
There you go. But that has to be, everything has a signature. So if they were grapes that were grown in a certain place, you can tell from looking at the spectrum here in a germanium counter whether those grapes actually came from that place or whether someone's cheating. And so,
already did that.
yes, they do that on a regular basis.
Found in the sea, right?
And the sea, they've done the salt, they've done a whole bunch of other things. So that they have these regular customers, and as well, of course, you can imagine a lot of other customers, archaeologists, anyone who wants to do dating. There's a number of at Sudan, we had customers from the Minnesota Pollution Agency. So they wanted some information on that. Anyway. Neutron activation, often called NAA, requires a source of neutrons first, which are usually reactors. So you go to a reactor, you take your sample, and it's placed in this flux, which is quite large for a reactor. It's sometimes you can get DT generators that are very high flux DT generators, usually never as much as a reactor though. You have neutron capture, and then there's the emission of gammas from the capture as the nucleus de-excites. And you might also end up with a radioactive nucleus which emits delayed gammas. So this is prompt gamma NAA and delayed gamma NAA for obvious reasons. If you're going to do gamma spectroscopy and look at it. So you start with all of that, but in the end you end up in a high purity germanium detector counting. You could do it in situ at the radiation site. That often happens, or at a counting facility. So Alabama, for example, and LZ, I think, uses Davis. There's a number of universities that have become centers for this kind of thing. You need a bit of radiochemistry, so when you get your sample back, it's hot. You might want to concentrate the material. I mean, you might actually do some chemistry so that whatever the product is that you expect to get from it, from the neutron capture, that you concentrate it and you put it into your germanium detector. And of course, you don't need a high sensitivity germanium detector because this thing's hot. And in fact, you don't want it anywhere near your very high sensitive germanium detector because it's just that. Okay, and then this example, count neptunium. And this is a 2.36 day lifetime PA. What's that? Anyway, it's one. This is also is commonly palladium. Palladium. Oh well. The technique is, of course, limited by the nuclear properties of the trace element that you're looking for in the material. So only about 60% of the elements activate, and so there are some that this technique just doesn't work for. And you don't want to be looking for something in a substrate that itself is highly activated, because then it will be masking what you're looking for. The LZ program at UC Davis used NAA to screen their radio pure titanium. They wanted to get really good titanium for LZ, and they used the McClellan Mark II, and they did their radiochemistry through at UC Irvine, and they also use the Triga at Irvine. So there's a number of different places that you can get the reactor, and it comes back to your institution. And they used a commercial high purity germanium detector, no need for it to be really sensitive, but they did put a Compton veto on it. Oh, and this is just continuing with that. You have scandium and titanium, so you have, this is the reaction that's occurring, and you get these isotopes, and this is the daughter that you get, and then you'll notice that all of these red peaks give you a very detailed fingerprint for the material that you're looking for and how much there is of it. Alpha counting, if you want to do that really sensitively, there is a company, California, called XIA, and they have made about a dozen of these and no more. And as far as I can tell, there are now as many as 5 around in various places, but not more than that. And I know they're talking about getting one at Snow Lab, but I don't think they have yet. So it's a basically a large chamber. The sample comes in here, and it has a, can't see it on here, but it has a trigger. It's basically a proportional counting chamber, right? And it's I don't really have a good picture of the wires, but it has a sample area and a veto area built in. And you're getting down to a sensitivity of 0.2 alphas per detector per day. And for our detectors, this is sufficient. The one thing that this was limited by for a long time was the tray itself. The only way that we can get down to the sensitivity we need is to create electroformed copper plates that are like a sample tray that we put in the sample tray and then put our sample on top of.
So that's the CD in the previous slide.
Yeah,
That's
actually,
the goal,
that's the old goal, actually. So I wanted to go fast by this one. I think it's more like, nowadays we want it to be more like 0.1. But our detectors were actually already at the goal at Sudan. Our backgrounds at Sudan were coming from the housings, the copper housings of the tower, not from the detectors. So we can just do, if we just do as good as we did at Sudan, we'll be fine. There's something called a beta cage, which is There's two of these, actually. There's a U.S. prototype, which was developed by Caltech in Syracuse, but now is continuing it in South Dakota, and a Canadian prototype at Alberta. And it's a screener for low-energy beta emitters, basically, but it also does a good job for alphas. It's neon gas time projection chamber, basically. And it has multi-wire proportional chambers, and this is a better picture. The XIA is kind of similar, but this is, you have a tray that comes in here, and if you look, what this is a picture of is everything that's listed, A, B, C, D, are all the different backgrounds that you can eliminate by seeing the tracks themselves and seeing whether they come through this trigger region or whether they start in here or whether they go both through both sets of wires. So these are the ones that you do care about, and you can get rid of most of the background. And it should do a factor of 200 better than the XIA for the alphas. But it can also do betas with the neon and with very, very thin walls and just wires here. Oh, these are some of the things that, oh, okay, this is some of the details. The backgrounds to the beta are photon induced, basically, so you do need a shield when you want to operate this beta cage, and it should be underground if you want to do it right. So they will, all of these beta cages will be put underground eventually. And you have to worry about all of the components, copper, the frames themselves, and you worry about the lead in your shield itself. The alpha background are the radon daughters, so that there was a lot of work done to electropolish the wires themselves, and again, it's this radon plate out that gets on every wire. Because you're stringing these somewhere, you need to actually build it, and that's why it's difficult. You don't have human beings standing around in a nitrogen atmosphere building wire chambers, usually. And this is, okay, what else do I want to see? This is just the radio pure construction and what the major backgrounds were for the beta cage. Radon emanation chambers. A simple one at Bulby is quite useful, and you put your test sample in basically a jar, and it emanates the radon, and then you count the radon. All right, but you can be a lot more sophisticated with it. This is the one that they use for Super Nemo, where you have several charcoal columns that are kept very cold, and the emanation chamber is after the first charcoal column. Put your sample in there, and the what gets emanated goes through a silica gel and another charcoal column, and you actually trap the radon inside of this column, and then look at it in a radon detector, which might be a scintillator. In this case, it is. And if you want to get really fancy, you can add timing to this whole thing. So this is, if you hear about something called a BIPO detector, this is something, a number of, there are many, many ways to realize this. This is the one that Super Nemo uses. If you look at the chain, this is the bi, this is the po. So the bismuth has a beta decay to polonium, which then alpha decays down to lead. So if you have, this is two scintillators, so you have the beta decay occurring at one time, and then in the opposite scintillator, if it were this chain for thorium, then you would see another signal 299 nanoseconds later, the uranium chain is 164 microseconds. Mass spectrometry, I promised I'd at least define all of these different kinds. But basically, you are just trying to tell the difference between the ions by moving them through a magnet, and then you see the mass to charge ratio being picked off by Faraday collectors or Faraday cups here, and you measure the current from a variety of channels, and that tells you, that separates basically how much of each of those mass to charge ratios there is for the element in question. It's really just a tracker in one sense. And all of this has to do with how you get the stuff into some sort of form by which these, this haze of droplets or this gas or whatever it is gets moved through the magnet. So inductively coupled plasma is used a lot. You create an aerosol out of a liquid, and then you spray it through an argon plasma torch, and that's what goes through, that's material. Or thermal ionization with a filament. You can use a secondary ion to sputter a surface. So say you want to look at a surface, you sputter it, release the ions, and that's what goes through. Glow discharge, and of course, actually using an accelerator. And this is often old nuclear research tandems that are used. And then the detectors are MWPCs or ion chambers. This tends to be quite expensive, and the rest are pretty much approximately the same. Our field uses ICP-MS a lot. So I've got a bunch more. Let me see what I think said. This is probably important because actually, again, most universities and geology departments and have ICP-MS. So you might think, oh, this is great. I have an ICP-MS machine here. I can go ahead and make some of the screening. I can set myself up as a facility. But it really, the sensitivity that they'll quote for you depends not only on the magnetic spectrometer and the sample dispersion technique, ICP-MS, low discharge, whatever, but it actually depends mostly on sample prep and handling. And pure and consistent blanks. And there's just, over time, PNNL, for example, has thought of all sorts of ways to get things into a liquid sample, including digestion and heat. And they recently worked with polymers in order to create some sort of soluble residue that then they can spray into their device. So they have, as the years have gone by, they have done better and better on, I know thorium, this one is, here's the thorium, is their big success story. So that's thorium and copper, so that they can actually, they make electroformed copper that's so pure that you can't tell how pure it is, unless you have such a good assay technique and your ICP-MS is good enough to tell that that's what's left in it. So they do both. They're trying to make ultra pure copper by electroforming, and then they needed to develop a way to find out how well they'd done with their electroformed copper. And that's when, and there's a lot of radiochemistry involved here in order to know exactly what was being put into their ICP-MS. Generally, germanium is a counting, and it's great. You take this big thing in here, you stick it inside of your sample cage, you go away, you come back a month or so later. Throughput is not great, right? And you need a large device for high sensitivity, but then you take your device out, your sample out, and it's still good to use somewhere else. Whereas ICP-MS is a completely destructive assay, but you only need a little bit of it, and you can get your answer pretty quickly. So I don't think we have to go through all that. Here are the sites for in North America where they have low background characterization of various types, either quite a few of the high purity germanium detectors and banks of them, or specialized. And it doesn't all have to be an overburden. So the dark ones here are all ones that are in mines or underground. But even a small overburden can do a lot. So that's LBNL and Oroville and PNNL have very shallow underground labs. And then a number of these other places have made their name in NAA, for example, where they send stuff off to reactors. And maybe there'll be one in somewhere here at some point soon. I think it's very important that we have as many as possible. It's not as if we don't need more. And also people can specialize in one form or the other, and that's often very useful.
And interdisciplinary is the key, right?
Pardon?
Interdisciplinary is a key.
Yes, and we'll be talking about that tomorrow, but the way to keep this thing going is to find your customers, because you need another. Physics is, the money is limited, and if you actually want to also employ technicians who will be there and have their own expertise over time and continuity there, that you need a customer base. But it's something that with a little bit of effort you can do. I don't think I need to do much more. Let me see, this is just that it's not just assaying, it's purifying stuff. There's a lot of different ways to do that. I do want to mention, because it's really important, that getting rid of the krypton 85 from xenon is a purification process that is done by distillation and adsorption. So you start by getting rid of impurities in the xenon, and then eventually you have to use distillation to get rid of those that's boiling points are lower. And just I just wanted, just to mention that, what the magnitude of the problem is shown here, because commercial xenon does go through this kind of a process on their own, and they reduce it to about 10 to the minus 7 mole per mole. Well, that's sitting up here, and here's where a WIMP signal is going to be, so that's clearly not sufficient. You need a krypton to xenon ratio of less than 10 to the minus 12 mole per mole, and that's why typically these experiments build their own purification systems. And you have to do it with argon too. And the one additional interesting thing about this is that when the argon-39 is coming basically from argon above the surface, and again, it's a cosmogenic type of a thing. There have been a lot of studies on it. Let's see, it's caused by spallation of cosmic rays in argon-40. But, so that means that you might expect, and it turned out to be true, that by looking for argon in deep wells, so going out to a place where there are actual mining operations, and getting the stream of, accessing the argon directly from the stream of gases that they're taking out of the well is the way to do it. But you actually have to look around for which well has the lowest uranium thorium. And so after an exhaustive search of different wells, Darkside chose Doken in Colorado, and they actually built an absorption unit on site so that as they brought the argon out, so they would concentrate the trace argon in these exhaust streams, and then on site they would use an adsorption columns here, probably zeolite or something like that. And then a distillation column was built at Fermilab to do the purification. I believe now they are no longer using the Fermilab one, they're using the one, another one at Grand Sasso. Let's see, that's enough. I don't think I have time for any more. Okay.
Thank you very much. Are there any questions? Yeah.
Only one. For the xenon, there at some point with else said there will be a short. I mean, there could be a short age of xenon, right? The resources are limited for xenon, but for argon, that's not the case, right?
Oh, you mean that the decay has a long lifetime?
No.
What do you mean?
The use of argon and xenon in industry and other applications is not the same, right? And xenon, there are only the reserves have a few tons, right? At some point, LZ will use like 20% or something, right?
I think that's true, yeah.
But argon, that's not the case.
No. Argon is a renewable resource? Not really, but in any case, xenon is expensive and there's a limited supply.
Yeah, that's thinking towards, I don't know, the 100-ton or 150-ton detector of argon. That would be viable, right?
Yes.
Also, the space, the
Well,
parameter is different, right?
Right, and so we don't know, how many of these wells have the lowest argon. So that's just a caveat. I think what you say is true, but it could be that either only a few wells that have depleted argon-39 at the level that they need. And so you may have a limited throughput for the supply.
More questions? Nobody more questions?
I was asking all the time.
Yeah, you can keep on asking, no problem. Well, if not, let's thank Priscilla again for a very nice set of lectures.
And, but I should also say that we've very much enjoyed our time here, and we should thank you and all the organizers for such a wonderful for time for us too. We enjoyed it, and maybe a round of applause for you guys.
Well, yeah, I want to thank all of you for the very nice set of lectures. As I have told you before, we wanted to get not only good lecturers, but approachable people, because we want to set up an astroparticle physics group here. And I think that our mini workshop fulfilled our expectations. So we started talking about things, and I see young people interested here, and so on. That's more or less what I expected, a core of 20 to 30 people here, which would be interested in, in getting to projects. So I think we managed to get our goal. So I'm going to give you a small certificate of attendance, but it's something we do always in Mexico. So this is for, sorry, but that's we're required to present one. So we also give one. So here is for Priscilla. It's just a letter. Thank you very much. This is for Alejandro. Where is Alejandro?